Welcome to The Explainer. Today, we're going on an incredible journey, an outward to inward journey. We're going to trace the breathtaking arc of the space age. Think about it. We started with this explosive, brute force engineering just to launch rockets into the dark. And now? Now we rely on this silent, invisible satellite infrastructure that literally powers and protects our daily lives here on Earth. It's really the story of how leaving our home is exactly what allowed us to finally understand it. Okay, let's dive into this. First, we'll look at escaping gravity's pull. Then, we'll cover the giant lunar leap. After that, we'll explore our silent satellite infrastructure, and finally, wrap up with how all this gave us a totally new planetary perspective.
So, Part 1. Escaping gravity's pull and the foundations of rocket science.
For centuries, rocketry was, well, mostly trial and error. Think of the simple Chinese fire arrows of the 13th century. But to actually leave the planet, we needed real math. The conceptual core dropped all the way back in 1687 with Isaac Newton's third law. Every action has an equal and opposite reaction, right? But it wasn't until 1903 that Konstantin Tsiolkovsky formalized the math for spaceflight. By 1926, Robert Goddard successfully nailed the first liquid propellant launch. And then, history took a dark turn in the 1940s. The technology was militarized to create the V-2 guided ballistic missile. It was built for war, absolutely. But this grim military catalyst inadvertently became our bridge to a new era, proving that rockets could actually reach the very edge of space. So, how do you actually hit orbital velocity? Well, Tsiolkovsky proved mathematically that you have to expel mass at incredibly high speeds. His brilliant workaround? Liquid propellants and multi-stage designs. By stacking rockets and then just tossing away the heavy, empty fuel tanks as the rocket climbs, the remaining ship gets lighter and much faster. It was a real game changer that maximized efficiency and made spaceflight mathematically possible. Moving on to Part 2, the giant lunar leap and NASA's incredible lunar milestone. Triggered by the launch of Sputnik 1 in 1957 and President Kennedy's stunning commitment in '61 to put a human on the moon before the decade was out, humanity aimed straight for the lunar surface. And this brilliantly illustrates what it took: 34 million newtons of thrust. That is the sheer, earth-shaking power of the Saturn V rocket. Standing over 110 meters tall, it remains the most powerful rocket ever successfully flown. Putting human beings on another celestial body required machines of almost unimaginable scale and power. But, brute force just wasn't enough on its own. We needed a stroke of engineering genius known as lunar orbit rendezvous. Instead of landing one massive rocket on the moon and trying to blast it all the way back up, they split the spacecraft. A command module stayed safely in lunar orbit, while a specialized lightweight lunar module went down to the surface. Afterwards, it blasted back up, met the command module in orbit, and everyone returned home. That exact choreography is what made the Apollo 11 landing feasible on July 20th, 1969. And the wild thing is, the ultimate success of Apollo 11 wasn't just a win for space exploration. It was a massive accelerator for tech right here on Earth. Solving those extreme lunar challenges led to huge leaps in material science, the rapid development of integrated circuits, and totally new frameworks for complex systems management. These tools, which were built for the void of space, literally became the foundation for our modern technological world. Let's move to Part 3 and see how this builds into our silent satellite infrastructure, including things like GPS. While the Apollo missions were these roaring, explosive spectacles, today's space age is really defined by quiet utility. To grasp this, we've got to understand orbit. It's not about escaping Earth's gravity entirely. It's a delicate balance rooted in Newtonian mechanics. A satellite is pushed forward at a specific velocity that perfectly matches the rate at which Earth's gravity pulls it downward. Because the Earth is curved, the satellite just falls continuously over the horizon. It is, quite literally, falling sideways forever. The vision for this was incredibly ahead of its time. Back in 1945, more than a decade before Sputnik even launched, Arthur C. Clarke proposed that placing just 3 satellites in geostationary orbit could enable global communication. And today, that exact concept is a reality. It enables everything from our transcontinental telecommunications to the real-time weather forecasting that protects our communities. Now, what's really interesting about this is how it powers the technology we rely on the absolute most: GPS. Your smartphone knows exactly where you are right now, thanks to a process called trilateration. Basically, your phone measures the precise, microscopic time delay of signals hitting it from at least 4 different satellites orbiting Earth. By calculating exactly how long those signals took to arrive, the system pinpoints your exact coordinates on the globe.
But to make that GPS system accurate, engineers had to account for some seriously mind-bending physics. Because satellites are moving fast and sit farther away from Earth's gravity, time actually passes differently for them. Clocks in orbit tick slightly faster than standard clocks here on Earth. If we didn't actively program the GPS network to correct for Albert Einstein's theory of relativity, the map on your smartphone would become completely inaccurate within minutes. You are literally carrying high-minded astrophysics in your pocket.
And that brings us to part 4. Gaining a planetary perspective through Earth observation and the Voyager program.
After conquering the challenge of looking out into the universe, we made this profound choice to turn our sensors back toward home. It's an incredible juxtaposition, isn't it? We kicked off with the roaring spectacle of massive rockets, brute force engines, and monumental moon landings. But today, the modern space utility is defined by silent, mathematical elegance. Things like multispectral imaging, advanced climate modeling, and the networks that guide our daily lives.
A prime example of this utility is the Landsat program, which kicked off in 1972. By using multispectral imaging, these satellites can detect patterns on Earth's surface that are completely invisible to the human eye. They map vital soil moisture levels, track the alarming retreat of our forests, and gather exactly the data we need. This isn't just about taking cool pictures from space. This information is the absolute cornerstone of our global climate models and the environmental policies we rely on to protect our local ecosystems. So the crucial point is that while we looked inward, we also sent robotic proxies outward, essentially birthing the field of comparative planetology. Mariner 2 gave us our first close-up study of Venus. Then the iconic Voyager program launched in 1977 and totally shocked the scientific world by discovering active volcanoes on Jupiter's moon Io and subsurface oceans on Europa. By studying these extreme alien environments, we gained a much deeper understanding of the unique geological and atmospheric processes that make our own planet habitable. But honestly, maybe the most significant scientific breakthrough of the entire space age wasn't a formula or a machine. It was a shift in our perspective. Think about iconic images like Earthrise, that brilliant blue marble rising over a dead, gray lunar horizon. It fundamentally reshaped humanity's perception of itself. For the first time in history, we could physically see our planet not as this endless, boundless world, but as a fragile, finite habitat suspended in vast, unforgiving darkness. The space age truly transformed the heavens from a realm of myth into a domain of systemic research. We've extended our technological reach so far beyond the atmosphere. But as we reflect on this outward to inward journey, it leaves us with a critical thought to ponder. Have we become a spacefaring species just to conquer the cosmic void? Or ultimately, are we doing this to use the profound tools of orbit to safeguard our future right here on Earth? Thank you so much for exploring this with me today. See you on the next Explainer.